Swayam Prabha. Digital India. Educated India.
So that is an intuition behind these second order necessary conditions. Let's move ahead. So we can now also include inequality constraints over here. So there are two kinds of inequality constraints at a given point. So let's say you're examining a particular feasible point X. There might be some inequality constraints which evaluate to a strictly negative value at that point. Right? So these constraints are going to be called inactive constraints. Inactive in the sense that if you move around that point in any direction, there is a small enough step size that you can still take and still not violate these constraints. Okay, remember we are assuming these are at least continuous, in some cases also differentiable, so they cannot just change suddenly. Right? So if at a point my function is negative, then in all directions around that point, there will be a small enough step that I can take and still the value will not be positive. So therefore, I will not violate that constraint. So I basically need not worry about these constraints at that point X, which is why we call them inactive. But there may be some constraints which evaluate to exactly 0. These constraints will be called active constraints. Why? Because we need to be careful. Careful in the sense, if we take even a small enough step size, let's say in the gradient of these gradient direction of these functions, as far as we take a small time step, the value is going to go positive. Okay, so there would be some directions which are sort of all aligned to the gradient directions that we should not take, and we should be careful there. So these constraints will be called active constraints. Okay, so this J is this index of the constraint number which signifies active constraints. Okay, so since they are sort of active in the sense the X evaluates to 0, we can sort of include them with the equality constraints. And then we say that X is a regular point of these constraints if all these vectors, the gradient of all equality constraints and gradient of all active constraints, right, they are linearly independent. The same reason, right, I can treat all these active constraints as equality constraints, and I would want all of them to impose an independent constraint. Okay, so this linear independence guarantees that basically. With that, we have sort of the main result, sort of called the Karushkunt-Tucker conditions. Of course, this is named after the 3 people who discovered them. These are again first order conditions, as you can see in the 2 equations below. Let us go through what these conditions are. Let X star be a local minima for the objective function f subject to equality and inequality constraints. And assume X star is a regular point for these constraints. Then there exists, once again it's important to realize that I'm talking about a particular vector, right? I'm not talking about any vector. There exists a particular lambda star, which is an m-dimensional vector because there are m equality constraints, and there exists another Lagrange multiplier vector mu star, which is p-dimensional because there are p inequality constraints. Okay, so one Lagrange multiplier per constraint, whether it is equality or inequality. The difference in the Lagrange multipliers for equality and inequality constraint is that for inequality constraints, the Lagrange multipliers cannot be negative. Okay, and such that these 2 equations are satisfied. Okay, to make sense of first equation is very easy, right? So there are some constraints which are going to be active. Those constraints I can include with the equality constraints, right? I can consider them as equality constraints basically. Once I do that, then that part of those gradients included with the gradients of h, they will satisfy the first order necessary condition for equality constraints. Am I making sense? So gradient of f plus I going from 1 to m lambda I gradient of hi x plus j belonging to the active constraints mu j gradient of gj at x star. This is nothing but the first order necessary conditions for equality constraints. This should be 0. That is something we have seen earlier. For all inactive constraints, what I can do is I can set mu j to be 0. Okay? If my jth constraint is inactive, I can set the Lagrange multiplier to be 0. Once I do that, then this equation 1 will be satisfied. All right. So that's the first condition. The second condition means basically this is what is called the complementary slackness condition, or I think the Slater's condition. Slackness. Which means that if a constraint is active, then the associated Lagrange multiplier may be non-zero and would of course be positive. But if my constraint is inactive, then the associated Lagrange multiplier has to be 0. Right? Remember, mu cannot be negative. You may be thinking, well, some values mu I gi may be negative, some values mu k gj may be positive. They may be able to balance out or cancel out each other. But unfortunately, mu cannot be negative. Okay, so if g is negative, the only way this is going to give you 0 is by setting mu j to be 0. Okay, remember, this is important. If my constraint is inactive, the associated Lagrange multiplier has to be 0. But if my constraint is active, the associated Lagrange multiplier may be 0, may be non-zero. Okay, both are possible.
Excuse me, sir.
Yes, go ahead.
If the set of constraints are inactive, then how can how can mu star be non-zero?
No, that's what I'm saying. If my constraint is inactive, right, which means g is negative.
Yeah.
In that case, the associated mu has to be 0.
Oh, okay, sir.
If my g is equal to 0, which means it is active, mu can be 0, but mu can also be positive.
Okay, so I got it. So thank you.
Okay? Yeah. Let us quickly try to look at why should mu be non-negative? What happens if mu is negative? So let's look at this simple example where there are no equality constraints. There's only 2 inequality constraints. Okay, and let's look at this point x0 over here. The blue curve marks points where g1 evaluates to be 0, and everything under this curve is points where g1 is strictly less than 0. Similarly, this red curve that you see marks points where g2 is exactly equal to 0, and everywhere below this curve are points where g2 is strictly less than 0. So what is our feasible region? Basically this, right? Now let's examine this point x0. At this point x0, which constraints are active? Anyone?
Sir, G1 and G2 are both inactive, sir.
Both. Both are inactive or are active?
Oh, sorry, both are active because at that point, both are 0.
Exactly. It lies on the intersect of these curves. So of course, G1, G2 both are 0. Therefore, both are active. Now, I want to show you why mu2, without loss of generality, why mu2 cannot be 0, or sorry, cannot be negative, and what would happen if mu2 were allowed to be negative. Okay, so let's consider, let's assume by contradiction mu2 is negative. Okay, then there exists a direction v shown by this black vector here, right? This vector v is the main defining characteristic of v is that it is orthogonal to g, this gradient of g1, okay, at x0. And of course, orthogonal to gradient g1, it could also have been in this direction, right? But this direction v is also positively aligned towards negative gradient of g2. Okay, so there is a small typo here. This should be less than, sorry. Okay, it points in the direction which is sort of aligned to negative gradient of g2, right? So with this, what happens if I take the dot product of this vector with this vector v? What would happen to this? Gradient g1 dot product v, what would that be? You know, I've already chosen v to be orthogonal to gradient
It will
g1.
be 0,
It has to be 0. What about v dot product gradient g2? Would be some negative number by assumption. Right?
Yes, sir.
Yes, sir.
And then that leaves us with, of course, gradient of f with v. So then the equation becomes gradient of fx0v plus mu2 times the dot product of gradient g2 with v. Right? But the issue is this is negative. Mu2 I have assumed is negative. This into this becomes positive, right? And then there is a negative sign here. So this becomes less than 0. How does that matter? Anyone? Why would that matter? What happens if I go in the direction of v? If I take a small step along v? What would happen to the function value?
The function value would decrease.
Decrease, right? So if the function value decreases, of course, x0 cannot be a minima. The second thing is, by going along v, am I violating any constraints? v is orthogonal to gradient g1. So by taking a small step along v, the value of g1 is not going to change. Therefore, g1 is not violated. How about g2? v is negatively aligned towards gradient g2. So if I go along v, the value of g2 can only decrease, which means it will still be a feasible point. Okay,
Yes.
so the conclusion is that there will exist a feasible direction along which the function value will reduce if my mu2 is negative. So that is why mu2 can never be negative for inequality constraints.
So this is because we had assumed that x0 is a feasible point. in the
Of
beginning.
course, yes, it is, right? Because I mean, the value of G1 at x naught is 0, value of G2 at x naught is 0. So it's perfectly feasible.
So because of the fact that we now get the fact, now the result is that it's there we can go in a direction which is uh, I mean because v is pointing in a direction where the curve is reducing, that means x naught would not be the minima.
Yes, yes. The
So
function value reduces by going along V, and we still remain in the feasible set.
so because we have to avoid the contradiction, we have to make sure that
Yes,
mu2 is going to be positive.
right,
Okay, sir.
right. So if mu2 is positive, you can see automatically what happens here. Right? It becomes greater than 0.
Greater than 0, which means
Then
going a direction.
mean is
Uh,
only going to increase the function
yeah,
value.
yeah.
All right. So that's why your Lagrange multipliers associated with inequality constraints have to be non-negative. Okay, so that takes care of it. There is also a second order necessary condition here, and it is basically the same as the second order necessary conditions for equality constraints. Basically say that this Hessian of the Lagrangian with respect to only x, okay, that has to be positive semi-definite on this. So this is a notation that I have not introduced, but this is basically the same. This would have all v which are orthogonal to your equality and active constraints. Maybe I should write it this way.
So what does KER stand for?
Once again, KER is kernel. Kernel is basically sort of null space. You can think of it as null space. Are you familiar with null space?
No, sir.
No. Okay. So if I have a matrix A which is m cross n dimensional, all vectors x such that A times x is the zero vector, this forms the null space. So in this case, it would mean that all vectors which are orthogonal to the gradient. This is confusing you. It's like for
Yes,
all
sir.
these.
It's little difficult to understand.
Okay, would this make more sense? All vectors v which are orthogonal to the gradient. And for you, it should mean all vectors v which are sort of not violating my constraints.
Okay, sir.
See, because gradient of h means it gives you a direction in which
It,
the function h will increase the most. If I go in a direction orthogonal to it, the value of h remains the same.
yes.
So by going in a direction orthogonal to the gradient direction, I'm not going to violate the constraint.
Yes, sir. And the dot product of the two vectors will be 0 because they're
Exactly.
orthogonal to each other.
Yes.
Okay, sir.
Okay. So that is the second order necessary condition. Now I am in a little bit of a dilemma given the amount of or given the amount of little time that we are left with. Maybe I'll propose two things and you guys can select the one that you want. So as far as optimization is concerned, I think I'm done with whatever topics I had listed in the course module. But I had several interesting other things in optimization to teach, especially convex optimization, which is sort of also are quite old algorithms, 60s, 70s, but they have now found their actual use in machine learning. You basically name any area and they would be useful. If I sort of do this, then I will not be able to do vector spaces at all. So if you want me to do linear algebra or vector spaces, then I'll have to skip this. If you want me to do this, then I'll have to skip linear algebra. I cannot do both given the amount of time that is left. I don't know. Is there a way in which you can maybe, let me see. Can I sort of do a poll or something like that? Okay. Those of you who want to sort of look at optimization, maybe you can raise your hands. I should be able to do a quick count on that. If you want me to go through convex optimization, please raise your hand. If you want me to do linear algebra, do not raise your hands. I'll give you 1 minute. Decide. Of course, I will share all the slides. Okay, slides will be available for both linear algebra part as well as optimization part. So I'm not going to take away slides from you. Okay, there are a lot of. I hope the rest are still with me. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. 12 want to do optimization for 13. The rest want to do linear algebra. Sort of split almost in the middle. And there are about 28 participants, I think. Okay, I think let us try to do optimization. And then in the afternoon session, there is a very small lab given to it. And it's on linear algebra. So maybe we'll look at the linear algebra aspect along with the lab. Let's continue with convex optimization. So even for me, it is more interesting to teach convex optimization. Vector spaces is, I think, all of us have taught that earlier. Okay, those who have raised your hands, you can lower your hands. We'll continue with optimization. And the thing is, as of now, what we have derived are given a point x, which anyone claims to be a point of minima, you can test whether that claim is valid or not. But the question is, how do you go about finding such points, right? You cannot try these conditions on any and every point, right? That would be madness. So how about, first of all, how to find candidate points that satisfy these conditions? These are what I call algorithms to solve optimization problems. One may think, or someone may say, well, I have these first order conditions. X and lambda can be my variables. I will plug in my functions f, h, and g, whatever are given to me, and I will solve for x and lambda. Well, that's fine as far as your n, right? The number of variables is maybe 2 or 3. These days, if you look at machine learning problems or geometry processing problems, problems in finance, for example, as someone said he or she is interested in, the dimensionality of the data is huge. For example, if I want to find the optimal mesh, typical mesh may have thousands of vertices, right? So these equations are, to solve these equations is easier said than done. You cannot just go ahead and solve these equations directly, especially when the dimension of these problems is huge. So you need to have good algorithms, right, that figure out what are the good points, right, points of minima or maxima. Second thing is you need efficient algorithms that give you these points. Just because the dimensionality is so large, I mean, yes, if you propose a theoretical algorithm, good. If you prove that it converges, good. There's no worry about it. But in practice, when you implement it, and if it takes days to come up with your points, then it's useless. Okay, so there are two things here. One, we cannot solve these equations directly given the dimensionality of the data, and of course, remember all these functions f, h, and g are going to be nonlinear. Okay, so even for a two-dimensional or three-dimensional optimization problem, you may find it very difficult to solve these equations. You need to have algorithms first of all, okay, that give you points of minima. Second, you would also want these algorithms to be proved that yes, if I use these algorithms, theoretically it is well justified. That's point number two. Point number three, they have to be computationally efficient. In other words, they should, if I start at a particular point, I should reach the minima quickly. Okay, all these three aspects are important. Just to give you a brief idea on algorithms. Okay, so I just want to give you an overview of this area of convex optimization. I'm not going to give you a list of algorithms. I'm not going to give you proofs that these algorithms work. I'm just going to give you enough material that you can start exploring yourself. Okay, so for now, let's consider only inequality constraint optimization, no equality constraints. Okay, so you want to minimize fx. You have a set constraints and you have inequality constraints, p of them. If you also have equality constraints, what you can do is you can, and let's say this is only one equality constraint, you can treat this as two inequality constraints, right? How? Saying that you want hx to be less than equal to 0, and by saying that you want hx to be greater than equal to 0. Right? So this would be your one inequality constraint, and this can be rewritten as minus hx is less than 0. So your minus hx would be your second inequality constraint. Okay, so in general, I'm going to look at only inequality constraints. The algorithms are a little different, but not much. So this is the problem. Okay, I want to minimize fx such that gx is less than equal to 0. Now, let me rewrite this optimization problem in a slightly different way. Okay, this is what we started with. Let's try to see how can we get this thing, right? So let's look at only the first part. This is the function fx plus mu transpose gx. I am going to ignore the inf for now. I want to maximize this, not over x. Okay, remember, I want to maximize this over all non-negative mu's. Okay? What would happen with this? First of all, why do you think mu has to be non-negative? What happens if mu is negative? Let's first clear that question out. And this is again another way of explaining why inequality constraints have non-negative Lagrange multipliers. What happens if mu is negative? What would
So
be
then,
the suprema?
then the point x would not be a minima.
No, forget minima. All I'm asking is what would the value of this turn out to be? If mu is allowed to be negative. See, you would have feasible points, right? So there would be x for which gx is, let's say, less than 0. Yes or no?
Yes, sir.
What would happen to mu into gx if mu is allowed to be negative?
Yes, sir.
Remember, it would be,
It will be negative.
so mu, of course, that is what I'm giving you, that I'm giving you the freedom to choose negative mu's, and now I ask you to maximize this function for mu's and where mu is allowed to be negative.
The maximum value would be f of x, sir, where mu is 0.
No, why? I can
Because
take a very sort of a large negative mu, right? If there is a point x for which gx is less than 0, right, I'm only going to increase it, right?
okay, sir.
Right, and what would be the maximum value if mu is less than 0? You can make it as large as you want. So
Infinity, sir.
Right, so that's sort of one reason why we do not allow mu to be negative. What happens if mu is greater than equal to 0?
So
Mu is greater,
at 0 it would be f of x.
right? But I mean, what is the maximum that you can get of this function, not of fx? Problem I'm asking you is maximize or obtain the supremum of this. See, if my gx, right, if my gx is negative, then what value of mu would this be maximum?
Mu is equals to 0. Maximum
Right?
is f of x.
So, exactly. So if g is negative, by choosing mu equal to 0, I'm maximizing this and I get fx. Agree?
Yes, sir. Yeah.
So you can see that this is basically the same problem.
Okay.
Right? Supremum of mu, supremum over all non-negative mu's of this, as you just said, is nothing but fx. This fx is then followed by the same thing, inf over x in x. So it's the same problem, isn't it? I'm just rewriting it in a different way.
Yes, sir.
I hope it makes sense.
Yes.
So this function in this bracket is nothing but something we have already introduced, right? This is your Lagrangian.
Oh, okay. Yes, sir.
So then original problem can be written in this way. Inf over all x of supremum over all mu of the Lagrangian. Okay, and we sort of say that the minimum value of this supremum of LXU, just denoting it by P star. This, since this is sort of the original problem, right, we call it the primal problem. Now, what happens if I switch the order of supremum and infimum? So if you look at the primal problem, I'm first taking supremum, then following it up by infimum. Instead of that, if I first take infimum, then take supremum, what happens? Right, so I'm not expecting an answer from you, but I'm going to denote this inf of lxu, lx mu over x as a new function. So you can see, since I'm minimizing over x, the resultant will no longer be a function of x. It will be only a function of mu. Right, so I'm denoting that function as q mu. This q mu is what is called the dual function. Okay. Now the question is, what is the relation between D star and P star? Right. So Lx mu is given. Lx mu is given. If I maximize the right hand side for all non-negative mu's, I'm only going to increase the right hand side, right? So the value of L for a particular x and mu is always going to be less than equal to the maximum value of L over all mu's, right? That should make sense, I hope.
Yes, sir.
Now if I minimize both sides, it's still not going to change the inequality, right? That's going to remain the same. I'm minimizing both with respect to the same variable x. If you look at the right hand side, you get P star. And if you look at the left hand side, you get D star. Okay, so by of course taking a supremum, that's one step over here that I have missed. Right? By taking supremum on the left hand side, I'm still not going to violate this inequality. This D star, which is the solution to the dual problem, is always going to be less than equal to P star, the solution of the primal problem.
Sir, can you just slow down on the taking the supremum part?
The right hand, this supremum?
No, the left hand side supremum
This
that
one.
you introduced.
Okay. Okay. Now take supremum on both sides with respect to mu. Now the right hand side, of course, is no longer a function of mu, right? It's
Yes.
a constant P star. So by taking sup over mu of P star, you're going to get just P star.
Yes.
Right? This is less than equal to, right? For all values of mu, this inequality
Okay, for
is satisfied.
mu we are checking. Okay, okay.
Yes.
Okay, okay.
So since for
Sorry. I
all
was
mu's,
checking for it. Okay.
so that's okay. Right? So that is why this D star will always be less than equal to P star. So this relation is what is called weak duality.
Sir,
Sir, I think it suffices to see that since we changed the operations, the order infimum and supremum, this has to come out this way.
Yeah, but in the sense, even if I had written inf then sup and then change the order, then of course this would be opposite. So
Yes.
just to
Yes, sir.
sir, why are the two operations not commutative?
they cannot be. I mean, it's you're minimizing with respect to one variable and maximizing with respect to the other variable. Right? How are they commutative? If you're minimizing, then it's okay.
Okay, if you're minimizing with respect to independent
But
variables,
then it doesn't really matter, right? Which one do you minimize first?
oh, okay, sir.
But here you're minimizing with respect to one variable and maximizing with respect to the other variable. So therefore it cannot be commutative. But that is something we have proved here. Of course, I've not proved that this cannot happen. That is what I want to talk about now.
Okay, sir.
Okay. When do we have D star equals P star? If we have, then that particular instance is called strong duality. Before I answer this, I'll tell you how this helps. Okay, the way it helps is that now we have two ways in which we can solve the problem. This was the original problem given to us. Right? Instead of solving it this way by first maximizing over mu and then minimizing, I can first minimize over x and then maximize over mu. Any algorithm that sort of attacks this is usually called a dual algorithm. Okay, and also I hope you note what sort of a function is q mu. With respect to mu, what sort of a function is this?
Okay, it is linear.
It's linear and therefore it is concave.
We can, yeah.
Okay, since it's concave, maximization of concave functions, we know what is the advantage, isn't it?
Yes.
Any local minima is a global minima also. So that's the advantage of using dual algorithms.